Step 4 video. Calculate adjustments to cyclones and pumps. Let's go ahead and move over to Streamline. In the Step 3 video, we adjusted our Streamline cyclone model to achieve our target improvements in CSE. We were shooting for a circulating load ratio of about 430%, close to the survey value. And we wanted to add water to the cyclone feed to reduce the bypass of fines while maintaining good underflow density. We set up this new water balance at our target circulating load ratio in Streamline's CSE improvement sheet. We then ran a model scenario to figure out what D50C we needed at the cyclones to achieve this new condition at the new water balance. Let's go back and have a look. We chose to exploit the improved CSE by reducing the power draw of the mill while maintaining target tonnage and grind. If you remember, the survey D50C was 90 microns, and for our new improved CSE condition, we had to reduce the cut size to 56 microns. Now, in Step 4, we need to calculate what physical adjustments to the pumps and cyclones are needed to achieve this improvement in the plant. Let's start by looking at the model flowsheet in Streamline. We navigate there by going to Trial Models and then clicking on Model Flowsheet. Here, you can select which trial model scenario you want from the drop-down menu. You can see drop-down menu choice number 2. We didn't do a scenario for number 2, so there's no data. Select number 1, and there. Our model populates into the boxes. The model flowsheet updates the ore water balance with the conditions for the scenario. Note, the water balance around the cyclone is set by the targets you entered into the CSE improvement sheet. The scenario notes automatically fill in from the description you made for this scenario in the trial model summary sheet. It is often useful to compare the model flowsheet to the survey flowsheet to see an overview of the differences. I suggest you make a printout of each and have a look side by side. Okay, now let's move on to new cyclone selection. At the top of this sheet, you will see the scenario you previously selected in the model flowsheet. Always remember that when using the new cyclone selection tool, you need to select the model scenario of interest because the inputs into the PLIT equation, which we will review in a bit, are pulled automatically from the scenario you have chosen. You can also see that the scenario notes you made in the trial model summary sheet are also automatically pulled into the notes section of the new cyclone selection sheet. This is another reason why it is important to be clear in your description of each scenario. Here, it is clear that we are selecting cyclones for the reduced energy scenario that we modeled in scenario number 1. Scrolling down, we see the cyclone parameters at the time of the survey in the green boxes to the left. This information is pulled from what you entered in the survey data sheet. To the right, the white boxes are the new cyclone parameters you will enter to size the new cyclones. New cyclone pressure, D50C, and the target D50C are in green, meaning they are calculated or given values. Scrolling down further, we see a chart for checking the capacity of the apexes we have selected for the new cyclones. There are 2 dashed lines indicating recommended limits on apex size versus slurry flow. These lines come from a classic publication by Arterburn in Design and Installation of Comminution Circuits. The red circle shows where your current cyclone selection is, in terms of volumetric flow per apex, shown on the x-axis. In this case, there's no red circle because we haven't sized the cyclone yet. We'll see it once the cyclone data has been entered. Just above the chart, you can see the calculated flow per apex. This is in cubic meters per hour and also in liters per second. This comes from the total volumetric flow rate of cyclone underflow for your chosen scenario and the number of cyclones you select above. Clearly, adding a cyclone reduces the flow per apex and vice versa. Going back to the chart, if the flow rate for a given apex is too high, then the red circle moves down into the roping possible regime. This indicates that the apexes are too small or the number of cyclones in operation is too low. Roping is bad because the cyclone is no longer classifying efficiently. Unliberated coarse particles will start to enter the cyclone overflow and leave the grinding circuit prematurely. And mill density may also get too high for efficient grinding. On the other hand, if the red circle moves above the top dash line, the apexes are too big, or there are too many cyclones in operation. This condition will reduce cyclone underflow density, which is bad for two reasons. First, fines tend to go with water, and more water in the cyclone underflow means more bypass of fines into the mill, resulting in overgrinding. Second, dilute cyclone underflow means low ball mill density and poor grinding efficiency. Apex sizing is discussed in Module 8, and as I mentioned, in the paper titled The Sizing and Selection of Hydrocyclones in the book Design and Installation of Comminution Circuits. Okay, let's continue exploring by taking a look at the Plitt equation calculations at the bottom of the page. Recall from Module 8 that adjustments to D50C cut size in hydrocyclones can be calculated based on cyclone operating conditions and geometry using the empirical equation developed by Professor Plitt. On the left, the Plitt equation is arranged to calculate the hydrocyclone Plitt constant K from the survey cyclone geometry and operating conditions. On the right, the Plitt equation is rearranged to calculate D50C using the survey K factor and the cyclone operating conditions from your chosen scenario and the cyclone geometry you define at the top of the page. Again, Module 8 is your reference for these calculations. There are no secrets, the calculations can all be done by hand. But here, Streamline does the heavy lifting for you, which is nice, so we can focus on narrowing down our cyclone selection quickly, and we can evaluate a number of different scenarios with minimal effort. Finally, at the very bottom of the page, you see a reference to the pressure drop versus flow and vortex finder size equation, again from Module 8. This equation is built into Streamline. This is how the pressure is calculated for your new cyclone selection above. So now that we know how the new cyclone selection tool works, let's go back to the top and size the cyclones for scenario number 1. Our first input is the cyclone inlet type. This refers to the difference between old-style cyclones and what are called modern high-efficiency cyclones. Old-style cyclones typically had a feed inlet that entered at a tangent to the cylinder body. Most newer cyclones have what is called an involute feed inlet design. This design reduces cyclone pressure drop for a given operating condition and helps the cyclone separate coarse particles from fine particles in a more efficient manner. Streamline assumes a factor of 10% lower pressure and 10% finer D50C for a given condition when upgrading from tangential style to involute style inlets. The actual effect on pressure and cut will probably be somewhat different than this in practice, but the 10% value has been effective over the years for redesign purposes. The drop-down menu allows you to choose which inlet style you'll be using for this scenario. In this demo, old tangential style inlets were in the cyclones during the survey. We see that shown here. For this scenario, let's assume we were going to put in all new cyclones with involute type inlets. So we select involute from the drop-down menu in the new cyclone column. Next, we have to choose how many cyclones will be in operation. Note, this does not include spares, but only operating cyclones. You'll want to install spares in your actual plant upgrade to allow for maintenance and operational flexibility. In this case, let's start with the same number of cyclones as the survey. We'll put 6 in operation. Now we choose the cyclone geometry. Let's start with the same diameter of cylinder and inlet as the old cyclones. Refer back to Module 7 if you need more information about cyclone geometry and components. It has a list of diagrams and definitions. You can get cyclone geometry options from your vendors for the different models that they have available. It's good to have this information when going through the sizing exercise, so you know that the selection you make here is commercially available. For example, apexes and vortex finders come in a range of discrete sizes, so you may as well limit your inputs to what you can buy on the market. For this demo, I've looked up the cyclone height of the new cyclone, and it is longer than the old cyclones. The new height is 232.5 centimeters, so I enter that into Streamline. Now I'm left with choosing the vortex finder diameter and apex diameter. I'll start by entering the same value as the old cyclones. Now that the cyclone selection is complete, we can see the calculated pressure and D50C. Pressure is close to the survey, so no issue here yet, although we'd like it to be lower. But D50C is not on target. Our target is 56 microns, and the yellow box indicates that our selection is too far out of range at 62. Let's have a look at the apex sizing chart. Scroll down. Our red circle is on the edge of roping, but not too bad. Let's leave the apex alone for now and try adjusting the vortex finder to hit our D50C target. Again, let's make this change based on vortex finders available from the manufacturer rather than arbitrarily adjusting vortex finder diameter. A vortex finder of 6 centimeters is available from the manufacturer, so let's try that. Now we see the D50C go to 58 microns. This is pretty close to our target of 56. Cyclone pressure has gone up to 96 kPa. And if we check our apex chart, it says we're still okay. We didn't make any change to the apex. We may be on the border of roping here, but for lowest bypass and best mill efficiency, let's keep towards the bottom of the line. Of course, you'll need to use your judgment and plant experience as you make these selections. So, now that we've defined the new cyclones, we need to check to see if the existing pump system can handle the new condition. We know that the pressure has gone up, so we expect additional demand on the pump motor. Let's go to the top and click on New Pump Calcs. Once again, everything in Streamline is based on the Metcom methods you learned in the modules. In this case, Module 9, Slurry Pumping, is your reference. Streamline uses the Bernoulli equation to calculate the pumping system total dynamic head. Again, all of this is covered in Module 9 if you need a review. The notes from the scenario of interest, which you selected in the model flow sheet, all transfer into the new pump calculation sheet. Here we see we're still looking at Scenario 1, the reduced energy case, taking advantage of improved CSE. The Bernoulli equation is shown at the top of the page, and a simple schematic of a typical cyclone pumping system is shown. This should look familiar for Module 9. The inputs for total dynamic head calculation are taken from the scenario selected, and from the survey data sheet. There are 2 white boxes you'll need to fill in for slurry velocity and friction factor. If you remember from Module 9, for a given pipe diameter and volumetric flow, cubic meters per hour, there was a table giving V and HF factors. This table is built into Streamline, and if the values for your scenario fall within the limits of the table, they are shown on the right. If your scenario conditions or pipe diameter are outside the range of the tables, you'll need to calculate or look up the velocity and friction factors elsewhere. In this case, the table values are available, so I'll enter them into the white boxes. Now, pumping system TDH is calculated below, and we see that a total of 34.2 meters of slurry is our total dynamic head. This value will be used to evaluate if the pump and motor are capable of delivering this TDH. Scrolling down, we see the pump power draw estimation calculators. Details about this are also available in Module 9, and the basic equation is shown at the very bottom of the page. In the white boxes, you'll need to enter the pump efficiency, drivetrain efficiency, pump motor efficiency, pump motor power rating, and pump motor full load amps. If you'll note at first, all of these values are populated with the values from the initial survey. If you're not changing the pump motor or the drivetrain, you shouldn't have to adjust these values. You will need to check the pump efficiency at your new operating point on your pump manufacturer's slurry pump curve. If you're unfamiliar with how to do this, please refer to Module 9. I checked the new operating point on the pump curve, and the pump efficiency was still 66%, so I left it there. Scrolling down, I can see that the pump is now drawing 84% of full load amps. So even though the pressure drop of the new Cyclones is higher at our Scenario 1 operating condition, the motor can still handle it. If the estimated power draw is close to or exceeds the motor capacity, then you would either have to run a new, less aggressive scenario, or consider upgrading the motor, and possibly the pump, depending on what you see on your pump curve. After you've redesigned your pump motor, and Cyclones, you may see an opportunity to squeeze a bit more CSE out of the pump, like we did in this case. Or perhaps you want to see what happens if you lift other constraints, like cyclone overflow percent solids. Now is the time to document your work. Make printouts and notes, then start the Streamline process over by going back to the CSE improvement sheet and set new targets. One of the great things about Streamline is it allows you to quickly explore circuit improvement options using a consistent method and proven models. Use CSE as your optimization metric, then take the benefits as your wish: more tons, finer grind, lower energy, or a combination of the three. Play with the demonstration files in your Streamline account to see how you can exploit CSE to get a finer grind or to increase tonnage. We've now completed a full iteration of the Streamline steps. I hope you found this set of tutorial videos useful, and please see the technical support section of your Streamline application if you run into any difficulties. Thank you for your attention, and welcome to Streamline.